If you've been doing any property testing in Haskell, raise your hand if you have. Okay, hands down. Raise your hand if you've been doing property testing in something other than Haskell. Okay, I feel like pretty much everybody here has done property testing before. Raise your hand if you haven't done any property testing. Let me find those people. Okay, so my last group. I'm sorry, this is not an introduction to property testing. I will try to justify and explain what we use it for a little bit, but you're not getting a tutorial to either QuickCheck or Hedgehog here. This is a comparative thing intended for people who are saying, all right, I've got this new project, I'm going to do property testing, I already know QuickCheck, why would I want to use Hedgehog? And how do they compare? What's going to hurt me, right? That's what this is mostly about. However, I will diverge if I need to, and I'm going to try to leave time for questions at the end, even though I have like almost 40 slides. All right. So, moving along. I already covered this not being an introduction, what this is for. You should understand the design of your property testing library. It affects the quality of your tests. So, talking about property testing a little bit, the idea is you state some equality or property. The property testing library helps you to write random value generators. They feed it into your property. It's some kind of function, you know. So I'll give you a quick example here. Is that readable, or do I need to be larger?
A little bit larger.
A little bit larger. We can do that. Is that better? Cool. So I'm going to be going back to this module called Humphreys Reverse over and over. Ignore the other stuff for now. So one of the canonical examples here is prop reverse, and I'll actually bring up a better example of that. So an example property you can write is things like, if I reverse a list twice, it should equal the original list, right? So if I bring up okay, so reverse, okay, list to list, right? So reverse 1, 2, 3, and then reverse of that returns the same thing, right? So this equals that, and that's true. So the function reverse satisfies its property. That's the kind of thing you can check. You just have to be able to state some kind of equality. The point of property testing is to make it so you don't have to write these example values, these test values. You just have, I mean, computers can generate random values, right? So why not have it generate random tests? That's the premise. There's extra stuff to it. We're going to talk about shrinking a bit. Shrinking is going to be one of the major differences in QuickCheck and Hedgehog, but that's the gist of it. So we don't want to write a bunch of manual tests. We just want to write some kind of equality or property that needs to hold for whatever it is we're testing, our component or function, whatever, and just generate the test randomly. Why might we do this? Well, how many of you have worked through the Haskell book, maybe up to chapter 18? Okay, so my book people, I made you do QuickCheck stuff, right? For monoid, functor, applicative, monad, typeclass laws. Okay, that wasn't originally in the book. We tested the book. We found that people were writing lawless instances that didn't work, didn't do the correct thing. Well, we're not going to just put in a paragraph in the book that says try harder. Instead, we actually added a whole new chapter and a fair chunk to each of those chapters telling you how to use QuickCheck for validating those properties. And then a lot more people in our test runs were getting the exercises correct, right? Why would production code be any easier than exercises in a book? It's not any easier to get it right, right? So a lot of people will think of property testing as just being about typeclass laws. Don't think of it that narrowly. It has much broader applications than that. Associativity, commutativity. Who's worked on like a streaming, like event processing or data system? I worked in ad tech for a couple times, so yeah. All right, so why might commutativity be useful in that kind of context? Well, if your fold or your function for processing the events is commutative, you can just parallelize your processing of the events and process them in any order, right? You don't have to have a serializable event processing order. But you should probably check that your fold function is actually commutative, the thing folding your events. Well, you can. You just write a generator for your event values, and then you test commutativity and see if you can break it. And that's what something like QuickCheck or Hedgehog is going to do for you. So, all right, who here has heard of Idris, Kak, Agda, Isabel, Haskell, PRL, new PRL? I'm losing you. Good. Okay. So, who has actually really tried to write like a little proof in something like that? Okay. Did you enjoy that? How long did that take you? The reverse thing. Has anybody tried to do that for like the vec type in Idris? How long did that take you? Hours. How long does it take to write that property in QuickCheck? Seconds. So, our bosses are not going to let us just spend unlimited amounts of time on proving our code correct. For the things that our types cannot encompass, QuickCheck is our half step, right? We're going to test more things than a unit test would. We're not quite to the level of types, level of correctness, or writing a proof, but it's a nice stopgap. And it can help shake out a lot of issues very quickly and cheaply, which, if you do prove that it's broken, if you use QuickCheck, you'll have a lot more time to fix it than if you tried to do it through Agda or something. And just in general, most software projects aren't valuable enough to merit full formal correctness. Let's just admit that. Everything we do is economized at some level, right? We have to economize our time. All right, so I'm going to mention things that do not work. I did a fair bit of research for this talk, including the general way people talk about property testing and the libraries for them. Some of those statements were pretty iconoclastic. It is not as simple as this is the best way to do things. It's not that simple. By the end of this talk, you're going to have a pretty good idea of what I think you probably should be using for property testing if you're a Haskell user. But it is not necessarily a trivial choice. There is no one best way to do everything. There are unforced errors you can make in a design, but it's kind of hard to pick a number one. And I'm going to try to mention the things that don't work because I don't really like talks that, just salesy, everything's fine, nothing's broken. And I don't think that's actually malice that people do that. It's because they haven't actually used it enough to know what's wrong. That's what you're getting a lot of the time. Not that I'm an expert in Hedgehog, just FYI. I've just been using it on some side projects. So Hedgehog started with Disorder Jack at Ambiata. Have any of you heard of Ambiata, Australian company? They have Haskellers. They do Haskell stuff. Yeah, I know. Nobody's ever heard of Australia. Okay. So Jacob Stanley invented it. I don't know how much help Jacob had, so I'm just going to call Jacob Stanley the author. That's Gistic on GitHub. Coworkers weren't writing arbitrary instances that had shrink functions. Default implementation for shrink is to return a list to an empty list, which means you're not shrinking. So what's the problem with that? Who here knows what shrinking is and what it's for? All right, we're going to need to explain that. Okay, so random data. Who here has generated some random data and looked at what it looks like? It's kind of messy, right? You've got this big gnarly data structure with these nonsensical values. If you've ever tried to use random data generation for fixture data, making up an invented user account, if you're not using something that uses lists of sensible looking values, the data's a mess. It looks like somebody just vomited on your screen. So when you do get a test failure, the first failure it gets will be some big, huge value that you can't really, you can't look at it and know, oh, this is why it broke my property. So for that, you need shrinking. Another reason to consider Hedgehog is that it ditches the arbitrary class. Don't worry, we'll get back to shrinking. So this is the arbitrary class in QuickCheck. So you have arbitrary gen A, shrink, A to list of A. All right, so with arbitrary, this is basically just a default gen value, right? So you're associating with some type A. So if we're talking about the arbitrary instance for int, we're associating two things with it using the type class. One is that we're giving it a default arbitrary value, which is just a random data generator. So the type of A is going to be int, so it'll be gen int, which means generator of int values, right? The shrink is an actual function, not just a default value. Nobody writes those. You're supposed to, but nobody does. And basically what it's supposed to do is it's supposed to take an A and return a list of values that are somehow smaller than the input value, okay? Now, what does small mean? Well, that's kind of part of the problem. It depends. What's the smallest, who here, all right, int in Haskell. What's the smallest int value you can think of? Min-bound. That's one answer. What is min-bound for int in Haskell? Negative 9 billion trillion whatever. Is that really small? Not really. Not for like human visual purposes. So you can't really actually categorically decide what the smallest value for something is. It might actually be domain specific. What if you want the origin or minimum notion of a value to be 0? And then you want everything out from that to be considered larger. So if you have a really negative number, it shrinks towards 0. And then if you have a really big number, it shrinks towards 0. Well, it depends. It depends on what you're doing, right? Now, shrinking something like a list or string is relatively easy. You just shrink towards like an empty string or something. But for other kinds of values, it may depend. So I'm not a big fan of the arbitrary type class. It's lawless. It's meaningless. If you've ever used data.default, stop doing that. And after you're done not using data.default, stop using arbitrary too. People have suggested laws for arbitrary. Uniform value distribution is one law they've suggested. Because that's usually what you want out of like a uniform distribution random function, right? Why might you not want uniform value distribution out of a generator? Edge cases. You want to check those first thing every time pretty much, right? So edge cases for a value like, or sorry, a type like int would be like, 0, -1, 1, min-bound, max-bound. You want to check like those 5 pretty much every time, right? So uniform distribution isn't really a great law. It sounds nice to people who like math, but for the rest of us who actually need to break our software, it's not very helpful. So before I go to uniform distribution, another reason arbitrary is annoying is because QuickCheck, the library, assumes you're going to be using arbitrary for all of your random generation. What if you have some big like record type, some like domain with a bunch of different fields in it? Okay, what if you want to try 2 different ways of generating values for 2 different tests on the same type? How are you going to do that? Typeclass is unique to a type. So there can only be one arbitrary instance for your record type. So what are you going to do? You could do type it. It's really annoying though. I'd rather just pass in different generators by parameter. Because you're having to create a new type of the whole type, not of the one field you want a different generator for. So why not just use functions? Haskell's good at functions. You can pass around generators as arguments to functions. We're already good at this. We're already good at the thing we need to just not use arbitrary, right? If you don't want to manually pass around arbitrary, use a reader monad. Do whatever you want. Okay, so yeah, we've already covered this pretty much. You don't really want uniform distribution. Okay, so the big selling point of Hedgehog is it has automatic shrinking. How does it have automatic shrinking? Well, it remembers what you generated, and it's maintaining a tree of what your random generator is spitting out. And then from there, it's able to say, okay, we started with this value, now give me the next thing, and then the next thing. And then it can work its way through the tree. I'll show you what the tree looks like, don't worry. It can work its way through the tree to automatically shrink values and treat it like a search tree, basically. Because again, when one value fails your property, you want shrinking to find the smallest possible value that still breaks the property. So you're not actually done when you've failed a property the first time. Your library, whether it's QuickCheck or Hedgehog, it's going to say, okay, we have one failing example, but we need to shrink from this. We need to find something else in the search tree that is smaller in some sense, but that also breaks the same property. Well, if it's a search, why not just have a search tree data structure baked into the library? So we've covered why shrinking matters. If you've got thousands of lines of output to your terminal, you're not going to figure out how to, how that broke your property, right? That's not readable. You need some like little one-liner, as much as possible anyway. So Hedgehog actually does have manual shrinking if you want it. That's one nice thing about it. It's kind of a porque no los dos. You can go with the automatic shrinking, or you can expand your shrinking manually. So does this look familiar from the arbitrary class? Remember, the A to list of A? You're just giving it a list of shrink options. So if it gives me a 3, I might give it 0, 1, and 2. Because in whatever generator I'm writing, those are notionally smaller than 3. It's whatever you want. And another reason manual shrinking might be useful is for regression testing or special values or special cases that you want to always check. You can use shrinking to inject those, or you could just make it part of your generator. Okay, so let's look at the Humphreys Reverse thing here a little bit. So I modified the original code. The original code that Tim Humphreys wrote. So Tim Humphreys is a maintainer of Hedgehog. The classic QuickCheck example is using list reverse. So the initial tutorial they wrote for Hedgehog was using list reverse, right? Just to show you like a one-for-one example. So the commented out thing there, that's the original. And it's using the monad under the property to basically grab random values out of gen int list. And then it's checking that reversing XS twice is equal to itself. And that's what that triple equals is basically a convenience function that says this should equal this, and if it returns false, fail the property. You don't have to use the triple equals. You can fail the property any way you want, but this is just kind of a convenient go-to. All right, so I modified it a little bit, and I wrapped list reverse in a list exceeded size function. And basically, it'll return a dummy value that'll fail, most cases, if the size is larger than this number. Otherwise, it goes ahead and applies the reverse to the input list. And there we go. We got it to fail. So this is what the output looks like. It's very fancy, colorful, unlike QuickCheck. Okay, so we've got some input lists that we got from our generator, genint list here. All right, so how many values is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, it exceeded size 10, so my property failed, right? So what's important here is it automatically shrunk down to the 11 element list. It could have barfed out something larger, but it didn't because it just automatically shrank it. If you look at genint list, so there's some differences in how QuickCheck and Hedgehog define their generators. QuickCheck is maybe a little bit simpler, but it's also less explicit. You generally declare the general size range or what range of values you want to generate in Hedgehog. In QuickCheck, you don't really do that by default. You can resize things. It has similar faculties there, but it just kind of assumes that you're just going to bind values out of arbitrary and then put something together. So it's a little bit harder to customize generator behavior, even for the provided ones that are baked into the QuickCheck library, than it is in Hedgehog. Hedgehog says, great, you want to generate ints. Okay, but what range of ints do you want to generate? And this can be a real problem. When I was comparing this list exceeded size thing, if you use the default generator behavior, QuickCheck would tend to dance around the 1 to 5 length list realm, and it never actually broke the list exceeded size property. It never broke it. I had to manually force it up to a larger, the QuickCheck generator, I had to manually force it up to a larger size that was going to break it. Since I already know what sizes I'm going for, I know exactly what kind of values my generator is going to generate. So I found some of the size stuff for Hedgehog to be a little bit puzzling for a while. And I'll show you what's going on here. So under the hedgehog.gen module, this is where you'll find a lot of your helper functions. And this is stuff that manipulates size, so you can just pass a size value and resize it to some size. Okay, so size just contains an int. That's what the size type is, just a new type wrapper for an int. Okay, what does size 0 mean? Size 50? See, I didn't know either. So I had to actually read through a chunk of the library source code to get a sense of the pattern. Basically, with 0, they're trying to shrink down to the smallest value that doesn't have any more shrinks. So that's all the values that return an empty list when you ask it to shrink the value. They generally max out around 99. 99 is going to be like your max bound for your type. So if that's word 8, that's 255. If that's int, it's the 9 blah blah thing. So 0 to 99 is the usual range you can use. You can have sizes larger than 99, but the convention seems to approximately be like that. All right, who can guess what linear means here? Or there?
Density doesn't really change besides along the range.
Yeah, it just keeps increasing at a linear rate, the size of the values. So they also have an exponential. So they'll slowly increase in size and then start kind of skyrocketing towards the end. And it just kind of depends on what distribution of values you want. Most people just kind of default to using linear. That's fine as long as you understand what the sizes mean and what kind of size of values you want out of the system. Okay, so who can tell me why all the numbers in my list are this ugly thing? Why is it that negative 9, 2, 2, 3, 3, 7, 2? Yeah, it thinks that's the smallest value for that type or that generator. So it shrunk the values as far as it could, and in this case we're using enum bounded. We're using enum bounded generator for our int values that we were stuffing into the list. The gen.list is basically a combinator for creating a generator of list values, and the arguments you pass it are the range of sizes of lists you want to generate, and then the second parameter is the generator for the values themselves. So since I use enum bounded, that's what I got. But I don't have to. If I use a different generator, I can have something that considers 0 to be the shrink target, the smallest thing. You just have to use whatever fits your case, right? Okay, so some limitations. Who here has used small check? Wow. Last man standing. Okay. So, small check's pretty handy if you have small data types. Now, usually when you talk about the cardinality of a data type, who knows what cardinality is? My book readers better have their hands up. All right, so cardinality is just how many unique values a type has. Remember how types are kind of related to sets? It gets back to that idea. So what's the cardinality of bool? 2. Whoever said 4? No, 2. False and true. Now, there is like a quantum bool. There's 3 values, you know, true, false, maybe, right? But no, just bool is just 2. So, okay, do you need to run 100 different tests in your property if the inputs are just bool? Probably not, right? If you have 1 bool, you only need to run 2 tests. If you have 2 bools, you need to run how many tests? 4. Because the arguments to a function, the cardinality is the product of your arguments. Curry, uncurry, right? Okay, so if you're going to do that, you'd rather actually just know that you exhaustively tested all possibilities. Boom, small check, use it for that. Do not try to use Hedgehog for that right now. Just use small check. It'll be easier and cleaner. So exhaustive testing is another thing worth keeping in mind. Now, int has huge cardinality, right? You're not going to exhaust all the values in int, unless you're Google. Maybe then you could if your test is really cheap. But generally, no. But the thing is, if you're writing Haskell properly, you're writing this domain type that describes your domain. And if you're just writing a bunch of enums and products of enums that describe various things in your domain, it might actually be possible to exhaust that domain. If that's tractable, and you can figure out whether or not it is by figuring out the cardinality of your type, go ahead and use small check. Then you don't really need randomness. If it's exhaustive, who cares? You're just running through all the options. Gen T applicative, it's splat equals AP right now, if you know what AP means. It's the way of doing the applicative apply in terms of the monad instance. Little slow, there's a PR to fix it, but it's not been merged. If you are an advanced user of property testing, like you've been using QuickCheck for the last 5 years and you're really like getting a lot of mileage out of it, using Hedgehog will be a little bit more annoying for you than people who are just casual users of property testing. You're probably going to have to patch Hedgehog. On the other hand, if you're an advanced user of QuickCheck, you probably already patched QuickCheck. So just keep that in mind. It is a lot easier to use Hedgehog correctly and not get properties that don't do things that make sense, that do things that don't make sense. And the automatic shrinking is actually really important. Just yelling at programmers to do stuff they're not doing, it's like abstinence education, but for software project management. Doesn't go anywhere, there's no point, just bake it into the tools or it's never going to happen. All right, so this is the real reason Hedgehog is popular. It has a little bit of hype in the Haskell community, I don't know if you've noticed. This is the main reason why. You see the green text, the syntax highlighting? That's how you sell a library. Just put some colors in the terminal and they will follow you forever. But there are good reasons for using it. I'm just saying most people's reasons for using it probably aren't super informed. All right, so Hedgehog is entish. It's just trees. You're just generating random trees. They're lazily generated. This is the underlying gen type. The gen without the T is just a type synonym for this monad transformer thingy. So the relevant part is just you go from size and seed. Those are your two arguments, and you generate a tree. So you know what size is. We've been talking about shrinking. Size does not mean anything concrete. It's relative to what the generator thinks size means. Your generator decides what size is. And then seed is just for the random generation. I don't know if you noticed, but when I had the property failing earlier, it said, hey, if you'd like to reproduce this test, pass in this size and seed. Right? Because that's all you need to reproduce a test. And then that's what tree looks like under the hood. It's actually a pretty simple representation of a tree, except for the monadic bits, the M that they have it all wrapped in. So it's a monadic like rose tree, basically. You just have a value at each node, and then attached to each node is a list of more nodes. QuickCheck, a little less going on there. It's just your seed, your size, and then your value, right? That's it. So any implicit structure or relationship between your randomly generated values and your shrinking is not represented in the types. It's up to you to do that correctly. So if your generator is size increased from 0 to 1 to 2 to 3 to 4, then your shrinking needs to match that behavior. You might not get quite the results you want. So enum bounded, sorry, did I have a question? No? Okay. So enum bounded says it shrinks, and it does, but it shrinks toward min bound, right? If that doesn't do what you want, just make a different generator. Decide for yourself. Okay, so another limitation of Hedgehog. You can't implement that promote function, A to gen B, gen A to B, for Hedgehog because of the tree representation. All right, you're probably wondering, why do I care? Well, if you look at it, it's basically saying if you give it a function that goes from an A and generates a generator of B's, then you have a generator of functions A to B. So you can randomly generate functions. Who thinks that if they were writing property tests that they may want to generate random functions? All right, you're wrong. So was I. Makes you feel any better. All right, so randomly generated functions are trash and they test nothing. I have tried to make this work. It is a waste of time. Cohen Clayson has good reasons for QuickCheck working the way it does, but I don't think random function generation is a good one.
Does that mean we don't have to learn to arbitrary anymore?
Yeah, I'm thinking about that one. All right. So just make something like a quadratic equation or something. Just something that doesn't spit out the same value, right? Like it could be like a monotonically increasing function over numbers or something. It doesn't really matter as long as it's not constant or identity. So this is one of the hacks that, and I think it's cutting off a little bit. That's fine. So one of the hacks I attempted, which I actually saw suggested on the Hedgehog issue tracker for randomly generating functions, was to use a data.map. And, you know, makes intuitive sense, right? A function a to b is a mapping from a to b. A data.map of a and b is keys of a that map onto values of b. Why couldn't that work? All right, let's see if we have anybody who's thought hard about this. Who can tell me why that won't work well? Well, so I handled totality with that default value. So follow on from that thought and tell me why it won't work well. Okay, let's think about domaining. Sorry, go ahead. Well, yes, you set the size. I know you can't see it right now with the range int thing, but you can set the size of the map. So you can decide how many inputs it has key value mapping for. But the size is the problem. So the larger the map you generate, the slower your property tests get. Dramatically slower. I basically couldn't go above 1,000 values in my map, key value pairs in my map, without it getting seriously slow. Okay, but let's think about domain and codomain here. What's the cardinality of int? Is it 1,000?
17.
Huh?
17.
It's big. It's much bigger, several orders of magnitude bigger than 1,000. So what's going to happen 99.9999% of the time when you use this randomly generated map to simulate a function with int values? You're just going to keep spitting the same value out over and over, right? That's not very helpful for property testing. All right, so you're probably thinking, if I use a quadratic function and that doesn't work for my property test, then how does this help me? If a quadratic equation or just something that just returns a bigger number than whatever it got doesn't work for your property test, then you probably have something more specific in mind, which means you didn't want randomly generated functions either. You just want a function that fits what you're testing better. So just do that. I did explore this a bit. I found Andy Morris's Hedgehog Gen Fun. It generated much better results than my extremely bad map hack. I actually measured the mean variance of multiple tests. Mean variance of data.map was 2.1 for a value range of 1 to 10. If you know anything about how statistical variance is calculated, you know that's very bad. Uniform distribution is 6. Hedgehog Gen Fun was 5.1. But that's for a very limited test. The Hedgehog Gen Fun implementation is really just a nicer, faster implementation of the data.map thing I did. So it's still going to fall back to the default value if you don't hit. Which means you probably shouldn't use it either. So another thing to consider with Hedgehog is they're pretty serious about implementation correctness. They actually recently added die-hard tests as a sub-project, or sub-package, I should say, to the project. Has anybody seen this before? Are they familiar with the concept of testing like randomness equality? Not equality, quality. No? Okay. Well, if you ever, now you know, if you got nothing else out of this presentation, you now know how to evaluate the quality of a random number generator. Congratulations. I didn't know it until I was researching this talk. But yeah, Gen Fun, same problems. Same problems as my data.map hack. So yeah, just don't do it. I discussed in a thread with one of the Hedgehog maintainers. He was right. I was wrong. This is dumb. Don't do it. Just define a concrete function and just use that. And don't use identity or const. Don't do that either, because it'll make a lot of things pass or that really shouldn't. So as a result of what I've learned, I'm actually going to change the library I've been maintaining. So it's called Hedgehog Checkers. This was my, I'm going to kind of kick the tires and learn Hedgehog project. Okay, my book people, you remember checkers? I'm just trying to port it to Hedgehog. So checkers is just a collection of default properties for common type classes, because nobody wants to write down the different applicative laws and property tests for them over and over. If we're all testing the same type classes, why not just have a library that tests all those type classes for us, right? That's what Connor Elliott's checkers was. So Andrew Martin has a QuickCheck classes library that does the same thing as checkers and Hedgehog checkers. It just has a bunch of properties that let you test, monoid, functor, applicative, monad, so on and so forth. But Andrew Martin didn't use arbitrary or random function generation. Andrew Martin used just the quadratic equation thing. And that was it. And that works fine. So I'm probably just going to do what he did. And then those are the two libraries I'm talking about. So some strengths of QuickCheck. If you have a really large state space or you need maximum possible performance, QuickCheck's probably going to be faster because you don't actually have to reflect what your generator is returning into a tree data structure. That tree can be implicit to the structure of your functions instead. And the less, if you've ever used Haskell, you know the less allocation you do on the heap, the faster it goes. So you can avoid some allocation if you're using QuickCheck. There is a way to run out of memory if you generate a kind of bad tree, basically, in your generator. It's not super easy to hit. There's an issue up for it. Just keep it in mind. So if you aren't sure what to use, you should probably use Hedgehog. But you don't have to choose one or the other. Hedgehog themselves maintain Hedgehog QuickCheck, and that lets you convert gens between the two libraries. So you can have a test suite that uses QuickCheck for a couple things that you need that for, and then you can have a separate test suite that uses Hedgehog, and then they can import the same generators and convert interchangeably back and forth. And that's perfectly okay. Do what you want. Okay, I'm going to show you a little bit of code and things I was kicking around to give you some better intuition of how this stuff works. All right, so let's look at linear tree here. So this is me just printing the tree representation of the generator. This is everything this tree generates at a size of 3 and with the seeds 1024, 1024. I gave it a range of 0 to 100. So given that, we didn't really get very far in terms of size. Because if our range on linear tree was 0 through 100, we're like just right at the beginning, right? The smallest values. But we can increase the size. There you go. So I went up to size 10. Now I have larger values, and then I work my way down to smaller values. Now, does anybody notice something maybe a little asymmetrical about the way it's generating values here? Yeah, it just keeps annotating like every node with an extra 0, right? It figures, hey, zeros it often fails stuff, right? So we'll just go ahead and check it all over the place. You don't have to generate it like this, it's just what the provided generator does. Okay. Now let's look at this one. Whoops. Bear with me. I'm going to up arrow, enter, and then I'm going to hit Control-C really quickly. There. Big trees. We got big trees here. Wait, I may have actually scrolled past where it ended. Hold on. Let me scroll slower. Sorry. I don't have like a good take function for just grabbing a chunk of it. Okay, so this one's an enum bounded tree of int values. And you can see how we've got our largest value at the top of the tree, at the beginning of the tree if you like. And then as we work our way down, we get to smaller values because you're shrinking towards min bound, right? Because that's what it's using for the generator. It's using the enum type class. Is anybody here not familiar with the enum type class? It's okay. I won't make fun of you. All of you are familiar with the enum type class. Okay. Whoops, I already did that. Yeah, so min bound of word 8 is 0, max bound is 255, right? And then it just lets you enumerate the values. Okay, so that explains that. All right, let's look at some manual shrinking. Those guys right there. Before I dive into the manual shrinking, It's 2:42, so I only have 8 minutes left. Does anybody have any questions before I give you a quick little... Actually, you know what? Somebody ask a question, and I'll do that in the background. Anybody? Yeah.
How, if at all, do you use the seed value and spit out when you
So generally speaking, your generator doesn't look that hard at the seed value. The random value generation takes care of that. Part of the reason for that is you need specialized random value generation for a library like this. It's not quite a normal random value generator. It's a splittable random value generator. Let me show you. Okay, that paper by Cohen-Clayson, splittable pseudo-random number generators using cryptographic hash functions. So your generator shouldn't really know anything about the random value generation. It should just figure out how to put random values together. Like for example, if you have a tuple, you're going to use 2 generators, one for each value in the tuple, bind the values out, and then construct a tuple. So you could do something like okay, so yeah, you can write a generator like that where you don't really fuss with much and you just reuse generators for whatever type is constituent to the tuple or the record or whatever it is you're doing. Who can tell me why I bound 2 values twice? Why didn't I just use A twice? Can anybody tell me?
The value would be the same.
Yeah, the value would be the same every time. So if that's what you want, you could do that. But if you want the tuple values to vary from each other, then you need 2 different variables. Because that's what it means for something to be a variable. Things that can vary independently of each other, right? So you need to bind twice and do an A and B. But if you wanted to only generate tuples that had matching pairs, you could very well do this, and nobody can stop you. Because that may make sense for some test you're doing. I don't know. Library doesn't know. It doesn't know your problem domain, right? Okay, so this one is intentionally broken. All right, so this manual shrunk 1 right here. Can anybody tell me why it just keeps spitting out 1 off into infinity? Well, so all right, so it hits.
There's no empty.
Right. There's no base or end case where it returns an empty list, right? It just always returns a shrink of 1 every time. So your tree just keeps going on and on and on. So don't do that. Make certain it terminates. And then this one looks a little more realistic, right? So our shrink function is right there. So if you give us 999, you get 0, 1, 2, and 3. If you give us 3, we give you 0, 1, and 2, so on and so forth. And it generates a tree that looks like that. So it'll test 1,000, and if that breaks, or even if it doesn't, it'll just keep going to the next value. All right, we have 4 minutes left with each other. Do we have any other questions? Doesn't have to be quite as zoomed in as this presentation. If you have more general questions about property testing, I welcome them. Yes?
In this case, you can test in 1000, just jump straight to the default case and go to the termination of the Trinket?
It could, yeah. So if you want a different behavior for that, you could do... So there's a slight conceit here. I know what you're getting at. the conceit here is I fed in the seed and the size, so I know what values it was going to generate and in what order. So I'm abusing that to keep the shrink function simple. And now you get more branching. All right. Any other questions? Okie dokie. Yeah.
I'm sorry. It looked like when you ran the test, sometimes you would get a seed at the end of it. When do you get that? I'm guessing you can reproduce the test?
Yeah, so whenever your property fails, it tells you, QuickCheck does this too, by the way. Whenever a property test fails, it tells you how to reproduce the test. Because you don't want to hope that a random number generator hits the same spot in the state space of values you were testing to break the test again, right? So it always tells you how to rerun the test. And it won't just give you the size and the seed. Let me rerun the prop reverse here. Yeah, there you go. So it tells you this failure can be reproduced by running that and then prop reverse. And it doesn't have to randomly generate anymore. Well, it basically doesn't randomly generate here. And it just hits that one spot in the tree to get that one failure. So you can keep checking the same failure over and over while you're trying to fix it. And then once you think you fixed it, you go back to using the full random value generation, and you see if any other breakages pop up. Does that make sense?
Yeah. So you'll use that somewhat frequently then?
If there's a breakage, yeah. You'll basically just pull it from your CI/CD, paste it into your module where you're working on your tests, fix it, do a full run where you're actually generating a bunch of values again. If it seems kosher, you push it up to CI, see if it goes green. So if you're interested in what I'm doing next, whatever it is, it'll be on lowerpub.com. I'll have a book coming up called Haskell Almanac. That'll be the next thing. I've got some other stuff to wrap up first, but that's what'll be coming after. It'll be an intermediate book focused on how to learn how to use libraries like Hedgehog or ASON. ASON's definitely going to be in the book because everybody needs to process JSON. We're basically just JSON mechanics, right? That's all we do. Front end, back end, I don't care who you are. We're all just JSON mechanics. All right, that's it. Thanks for your time.